Hello everyone, welcome to my channel Chemistry is Fun. Today we will deal with the topic Raoult's law. Now, this Raoult's law is a relation of the subject in physical chemistry and it has implications in thermodynamics as well. Here we will study that the partial pressure of each component in case of an ideal mixture of the liquids is equal to the vapor pressure of the pure component and is multiplied by its mole fraction in the mixture. This we will see slowly as we proceed in the video. And we will see that as a result of this, the relative lowering of vapor pressure of a dilute solution of non-volatile solute will be equal to the mole fraction of the solute in the solution. That is, we are considering a dilute solution in which the solute is non-volatile. Because of that, there will be a relative lowering of vapor pressure and that will be equal to the mole fraction of the solute in the solution. And now if we see the statement, then as per the statement, the partial pressure of any volatile constituent of a solution at a particular temperature, when the temperature is constant, that will be equal to the vapor pressure of the pure constituent multiplied by the mole fraction of that constituent in the solution. Means in the solution we have to first find out the mole fraction of that particular constituent, and that mole fraction will be multiplied to the vapor pressure when the constituent is pure. Then from here we can find out the partial pressure of any volatile constituent in a solution. Now let us consider there are two liquids A and B and we just mix them and get a mixture. So if we mix Na moles of liquid A and Nb moles of liquid B and we get a mixture. Now there are two components here, A and B. So both will be having their respective partial pressures. Let the partial pressures be denoted as Pa and Pb for the components A and B in the solution. For A the partial pressure is Pa. For the component B the partial pressure is Pb. But when they were in their pure states, their pressures will be Pa0 and Pb0. That is in their pure states respectively. So in that case, Pa will be equal to, we have to find out the mole fraction. So how we calculate mole fraction? If the mixture is having two components A and B, then Nb is the mole of B and Na is the mole of A. So we first find the total number of moles. So total number of moles is given by Na plus Nb. This is the total number of moles. If we have to find out the mole fraction of A, what we do? We do Na divided by total number of moles. So we get the mole fraction. So this part is the mole fraction, Na by Na plus Nb. This mole fraction, when it is multiplied by Pa0, Pa0 is the vapor pressure in pure state. Pa0 is the vapor pressure in pure state. Vapor pressure in pure state is represented as Pa0 and Pb0. So when we multiply the mole fraction with Pa0, we will get Pa. Okay. So Pa is the partial pressure of A. Pa is the partial pressure of the constituent A. Similarly, by multiplying the mole fraction of component B with Pb0. Now what is Pb0? Pb0 is the vapor pressure of component B in pure state. Pb0 is the vapor pressure of component B in pure state. Vapor pressure in pure state for component B. So when Pb0 is multiplied by Xb, we get Pb. What is Pb? Partial pressure of component B or constituent B. So when we add Pa and Pb, what we get? Total pressure. This P is the total pressure. So by adding Pa plus Pb we get P, which is the total pressure. Now when we substitute the values of Pa and Pb, what was Pa? Pa was Xa into Pa naught. So we write it here. What was Pb? Xb into Pb naught. We write here. So adding together we will get the total pressure. So from this we can say that this law, this Raoult's law, is a deciding factor. It will help us to decide whether the solution is ideal or non-ideal. If the solution obeys Raoult's law at every range of concentration, then it is an ideal solution. It should obey Raoult's law at every concentration, then it is ideal. But if either it shows positive or negative deviation, we call it non-ideal solution. At the same time, we can have a relationship between Raoult's law and Dalton's law. Now, using Dalton's law of partial pressure, we can calculate the composition of vapor in equilibrium with the solution. See, there will be an equilibrium between vapor and the solution. So, the composition of vapor which is in equilibrium with the solution can be calculated applying Dalton's law of partial pressure. Now, if there are again two components A and B, and their partial pressure of the vapors, now we are considering the vapors. The partial pressure of the vapors are now Pa and Pb. Okay, in this case, Pa and Pb are the partial pressures of the vapors A and B. Total pressure will be P. Again here, total pressure is P. The mole fractions of the vapors are Ya and Yb. These are the mole fractions for the vapors, Ya and Yb. So here Pa will be equal to Ya into P. What is P? Total pressure. P is the total pressure. So total pressure multiplied by Ya, that is mole fraction of vapor A, gives Pa. Similarly, Pb will be equal to total pressure P into Yb. Yb is the mole fraction of vapor B. So Pb, the partial pressure of B, is obtained by multiplying total pressure into Yb. Yb is the mole fraction of vapor B. But earlier we have seen that Pa is also equal to Xi into Pa naught. We have just seen when we are doing that Raoult's law. Similarly, Pb is equal to Xb into Pb naught. We have just discussed about that. So we can equate these two. This Pa and this Pa can be equated. So we get Ya into P. This pertains to the vapors. This side. Ya, this is for vapor. Mole fraction of vapor A. So Ya into P will be equal to Xa into Pa naught. Xa into Pa naught. Xa is the mole fraction of A and Pa naught is the vapor pressure when component A is in pure state. So from here we can just shift P to the other side, so it gets Xa into Pa naught by P, that is Pa by P. Pa by P, Pa, partial pressure of vapor A. Similarly, we get Yb is equal to Pb by P. So we can say that in case of an ideal solution, the vapor phase will be richer with more volatile component. If the component is volatile, it will be having a greater vapor pressure. In that case, in ideal solution, the vapor phase is richer with more volatile component with greater vapor pressure. Now related to this topic, we can go through one numerical. The numerical states that an aqueous solution having 28% by mass of a liquid A whose molecular mass is 140. It has a vapor pressure of 160 millimeter. Vapor pressure of 160 millimeter at 37 degrees C. Find the vapor pressure of pure liquid A. We have to find vapor pressure of pure liquid A. Given that the vapor pressure of water at 37 degrees C, same temperature, is 150 millimeter. So this is the numerical given. So we know that if there are two miscible liquids, total P will be equal to mole fraction of A into PA naught plus mole fraction of B into PB naught. We have seen when we were discussing the theory, we have seen that P total is equal to mole fraction of A into PA naught plus mole fraction of B into PB naught. Now for A number of moles they have given, it is 28% by mass. So number of moles of A will be equal to 28 by 140. 28% by mass of liquid A. So it is 28 by 140. So it will be 0.2. Liquid B is water here. So mass of water will be 100 minus 28 because rest is A. So B is water. Its mass is 100 minus 28. 72. Moles of B will be equal to 72 divided by 18. Molecular mass is 18, we know. If you divide, how much we get? We get 4. So total moles is equal to earlier it was 0.2 plus 4, that is for water. So we get 4.2. Total number of moles 4.2. Now total pressure is 160 mm. It is given. P total. (160 millimeter) given. For water, it is 150 mm in pure state. So PB naught is 150. So now PA naught we can calculate. So total 160 will be equal to, that is for A it is 0.2 divided by total number of moles 4.2 into PA naught plus 4, that is for water we have just seen, by 4.2 into 150. So we can just calculate using this formula. We can calculate over here. On calculation we find that PA naught comes out to be 360.15 mm. 360.15 mm. You calculate from this formula, from this equation, it is 360.15. How we can do this? This part 40 by, this is 4 by 4.2, 4.0, this is 4.0 by 4.2. So this full thing we can calculate and shift to the other side. So 160 minus this we can shift to the other side. and then we get PA naught. So PA naught will be equal to 360.15 millimeter, 360.15. I hope you could understand the topic and the numerical which I discussed today. Thanks for watching my video. Please subscribe to my channel. Thank you all. Please subscribe to my channel. Thanks.